my name is Alex. I'm an engineer and my passion is design, development and prototype production of all sorts of engineering solutions. In this episode we have to make something tiny, a tiny replacement part for a wristwatch. So this box may be 20 times the size of the part, I don't know. So either we machine that part successfully or I mess it up. Let's see about that. So the story goes, a friend of mine, a former work colleague from the university, he contacted me the other day and he has become very serious in watchmaking over the years, or rather in repairing of wristwatches, I should say. So the link to his YouTube channel that he recently started is in the video description below in case you're interested. So he contacted me and asked me for advice because he has a watch for repair with a broken part, and that broken part is unobtainium. So he asked me what he could do in that situation and so on, and I very naively said, just send it over, I'll give it a look and see if I can help you out. And I can see you already laughing through the viewfinder for my being so stupid and accepting such small parts for reproduction. But hey, let's see how it goes. Alright guys, heads up in the beginning, I'm not a watchmaker, so the watchmakers out there, you guys, please don't destroy me in the comments if I'm using the one or the other wrong expression here. But I'm just trying to give an overview of the problem at hand. So this here is a picture of a Seiko wristwatch, and to be more precise, the King Seiko 44KS movement. And the main actor in today's video is this lever here, which is called the second setting lever, so I'm told. And the purpose of this lever is, when you pull the crown in order to set the time, this lever pushes down onto this little disc here, the second setting disc, I'm told this is called. And the purpose of that is to stop the second hand so that you can synchronize watches like it was demanded by the military. Now the problem with this lever is, I am told, this lever in this particular movement tends to break here in the most narrow section. And what complicates this is that Johannes tells me you cannot source this lever as a replacement part anymore. And he gets that information from a friend of his who is either a watchmaker or a watch trader in Japan. And he tells him that this lever cannot be sourced as a replacement part anymore. Maybe because the lever tends to break, the replacement part stock has been consumed, I don't know. Please fill in the comments if you know something more precise. So consequently, Johannes has the problem that he received this movement with this lever in the broken condition, and with that part of the lever, the broken off piece, missing. So you see, he has two problems now. He has to get a replacement lever machined, and this is where I come into the game. However, I have the problem now that I am missing this piece here to take dimensions from. So I believe what I'm going to do is to use the part that Johannes sent me, so that's this part here, take accurate dimensions off of that with the profile projector, then overlay the dimensions onto this photograph here and retrace the dimensions of the broken off piece. So we are here at the classic Nikon V-12 profile projector that I have set up with a 20 times magnification lens. So the lever is on the stage, and just to give you an idea in case you're interested of how that works, that geometry measurement in a classical sense on such a profile projector. You see I have this overlay chart on the screen here that makes such a measurement task an easy feat. For For example, if we want to center out in that hole here to make this our origin, we just find the next corresponding circle on the overlay chart here, roughly like so. Sorry, I have to look in an oblique way onto the screen because of the camera, so it might not be very precise what I'm doing here. And then we zero out the DRO and, for example, measure what have you, the coordinates of that geometry in relation to the hole, like so, for example. Find the corresponding circle, then read the coordinates, and so on. Sorry if I'm not being precise here, but I'm just trying to make the point how you would use that instrument. Or let's say we want to measure the angle between this leg, this part, and this part of the leg. You can see the upper one is now nicely parallel to the chart, and now we can either find the next angled line on the chart and read which one that is, or we can tilt the complete screen grid in such a fashion and find a parallel until it's parallel with the contour, and then read the graduation down here on the screen. So you see, that makes measurement of such a tiny part really really nice and enjoyable even. Or let's say we want to find the center of that transitional radius here. You see, it's just a matter of seconds of finding the corresponding circle and then reading the coordinates on the DRO and so on. We also may use the top light feature here. This was backlight just before, and you see with the top light feature we can study the surface. Or, for example, we can measure a feature that has no through hole, like this pin location here. It's easy to find. You can see this location of that pin is eccentric in relation to the outer shape. This is something I'm going to discuss in just a minute in the video, so don't worry about this just yet. And I have to apologize. You see, this is a complete lever that we have on the projector here. So obviously this is the new one I made, and I have no other alternative than show you the new one, because believe it or not, after machining the new one I lost the broken piece in the chip tray of the lathe. So that's how it goes. I searched for about an hour or so, but I just couldn't find it anymore with the chips in the tray. Alright, sounds like a good strategy to get the exact dimensions of that lever. However, next the question arises, does it make sense to exactly replicate that lever, remachine that lever, considering that, so I'm told, these levers tend to break here anyways? So yeah, good question, I think. And in order to answer this, we have to understand, or at least think of, why is that lever so narrow here anyways? What's the purpose of this? And the only explanations I could come up with is either this is so narrow here in order to give this lever some springiness. If this is an actual English word, I don't know.
They picked springy! In your face, Patty and Selma!
Or it is so narrow here in order to give the watchmaker during the first assembly process the possibility to slightly bend this lever to accommodate for tolerances here, so as to give this contact point here an appropriate amount of force on the second setting disc. Now, I rather believe the second explanation is true, because if this was intended to give that lever some springiness, and I was the designer, I would have rather designed it in a straight fashion, like so, which would make more sense. And so I rather believe that the bending theory is true. I also believe this because if you look at the lever, you see it has a slight V shape here. And I'm having a hard time to believe that this V shape was there right after production, since this is a stamped sheet metal part originally. To me it doesn't really make much sense to stamp this part in a V shape here. I'm not sure, but rather I believe that this is a sign that the lever was bent in the first assembly process to work with tolerances here in the crown. So if there is any watchmaker out there who has exact knowledge about this, please be so kind and leave a comment. But for the rest of this video, I'm assuming that this is the purpose of this narrow section here. So consequently, I proposed to Johannes to make this section here slightly wider. So originally it was 0.25 millimeters wide, and I proposed to make it 0.35 millimeters wide, and to make the lever out of a slightly less hard material, so that in the end the remachined lever should have the same strength, being wider here, but out of less strong material. And due to the less hard material, it should be more ductile, that is, more resilient towards brittle fracture. The only downside of this is that overall the spring stiffness of the lever gets a little higher. So Johannes and I discussed this back and forth, and we came to the conclusion that it surely is worth the try. Alright, so here are the results of the profile projector measurements. In addition to the results I could gain from the photograph retracing. So the dimensions highlighted in orange are from retracing the photograph, the shape of the broken off and missing piece. So they are not exactly sure. And the other ones are as exact as I can measure them with the profile projector. So the only modification I'm going to do is to change this dimension, the center coordinate here, from 7.14 to 7.24. This should increase the width of that lever here from originally 0.25 millimeters to 0.35 millimeters. And thereby, in addition to making the lever out of slightly more soft material, it should give the new lever the same strength here as the original one had. So bending it here in this area should require the same effort as the original one did, given or assuming that that bending theory is true. And the new lever should be more ductile, that means less prone to brittle fracture than the original one, while still, and that's questionable, having a slightly bit more spring stiffness than the original one. And for the very quick ones among you who found that that hole, according to my dimensions, is off center in that section here, yes, that's actually true with the lever I received from Johannes. And I'm not sure if you can see it on camera, but here we also get a glimpse of the off-center position of that pin in that lever. And that photo is from another movement, so I assume this was constant during production, who knows why. And I'm going to do this eccentricity here in the remachined lever as well. If I recall right, then one of the masters whom I learned from, he used to say that the machine's table should be as clean as the Virgin's honey pot when you're setting up. I'm not sure if that's true, but I sure do practice that. Good old Walter UTA dividing head saved me a lot of times. Alright guys, on this project we really go all in on the material spill. Johannes, I hope you know that. And you're either gonna laugh at me for saving stuff like this, or raise your hand because you saved stuff like this by yourself. So let's start with this 4-flute solid carbide resharpened end mill. I'm only using a minimal amount of lubrication here. Firstly, not to flood the dividing head, and secondly, that's absolutely appropriate and enough given this material and the solid carbide end mill. Material I'm using here, by the way, is 1.7225 in a quench and temper state. The equivalent American designation should be 4140. Here I'm checking if the leg length is already sufficient. So this is just conventional milling that is roughing out the second leg to length, or to sufficient length, that is, and so that we have the corner right in order for the machining the transitional radius there. And here I'm machining a second phase so as to size the end mill, because I forgot to measure the end mill diameter before I started machining. So that's what that dimension is good for. And here I'm plainly using the DRO's radius interpolation function to radius interpolation mill that transitional radius. Here I already programmed one of the radii features of that hook end, and I'm roughing out material so as to reach the first 0,0 position. In case you think of this work as manual CNC, then the CNC stands for caveman numerical control, I guess. And here I'm machining down that straight portion. Here a different perspective, so this is machining the first leg to size and machining the end radius there. Of course I have to rough away some material first in order to do this. And this again is radius interpolation milling with the aid of the DRO. Simple as that. So here I'm machining that neck portion. The end mill is smaller than the radius that is supposed to be there, so that's also why I'm interpolation milling again. And now I switched over to a 4-flute solid carbide 2mm end mill in order to hog out the material with the tight radii on the inside of that part. So one has to be very careful, of course, with that thin of an end mill and that hard material. So I'm taking my time here, going very small steps. This is that angled line I'm interpolation milling here. And the nice thing about that interpolation milling is you can always deviate from the next 0,0 coordinate that you're aiming for, in order to rough out more material, which is kind of what I'm doing here. So you see the end mill has to take more and more material, so I'm deviating from the next target and roughing out a bit more and then going back to 0, 0. And this is that transitional radius. Okay, so far so good. Next is machining that step and that 14-degree angled linear feature on the top side, which is what I'm doing here. So let's check if overall the part is good. At least the existing side fits. And here's spot drilling those two holes. Next is drilling the pivot hole for the screw with this 1.5mm drill that I have in this drill arbor. That 1.5mm hole is really easy peasy in comparison to that 0.6mm hole we have to drill next. And for that purpose we have to make a drill arbor for that thin drill, because I have no collet that goes down to 0.6mm clamping diameter. So that's that 0.6mm drill. And I'm drilling a hole in order to glue it with Loctite into that arbor. Taking my time here, of course. Handling that thin of a drill is really no joke. It's like handling a wedding cake in one hand and a newborn baby in another hand, all under the supervision of the bride or so. So this arbor here for the 0.6mm drill, I back drilled it off camera just for the sake that I can wash it through properly and blow it out. If it was a blind hole, that would be much more difficult. Also, it would be possible that the Loctite drains all down in the bottom of the hole and I get hydro lock and cannot insert the drill the full depth of the hole. So that should be a fair chance for a good hold. So now comes the scary part, the 0.6mm drill. I hope the arbor is already, the Loctite in the arbor is already hardened. It's just been lunchtime since I glued it. So let's see, or let's hope that works. If it doesn't work, I have to re-glue it, but the nerve-wracking thing is that's the only 0.6mm drill I have left. Now doing this with the standard quill is really not the smartest thing, but I have no fine field quill. So you have to drill here only with the fingertips and feel every little change in the drilling pressure in order so that you can relieve the chips and re-oil the drill. This is all very, very thin for my clumsy hands, you know. Verdammt. So that broken off piece of twist drill is almost flush with the upper surface, and it's stuck in the hole, and of course there's no chance to getting this this ultra thin drill out here. So of course this was the next to last step in making the part, and this is usually where things go wrong. But let's try to make the best of it, and I'll try to saw off the part here. And in order to avoid cutting with the high-speed steel saw blade through the high-speed steel drill, which would wreck the saw blade, I'm going to try to cut like this around the broken off piece of twist drill in the hope of being able to part off one or two pieces and then be able to pull out the broken off fragment of the twist drill. So let's see if we can save our work done so far on this part. Yeah, axial runout is not perfect, but saw blades are saw blades. You know that as well as I do. Here I'm making sure that the thickness is right, because that's I get the impression that this is too thin, but let's see about that. That may be too thin, but let's see. So I've sawn off the first one, but now I have to reface it and machine the steps, so I would rather pull out the broken off twist drill if possible. However, now there is a ring of the soft material around it, which prevents the drill to be pulled out easily. So I have to gently try to file away that ring and judge the depth by when it gets hard.
Say what?
There's a bit of twist drill, but just a piece still must be stuck in there. Okay, so I refaced it, machined the step here, and well, let's hope for the best and give it another go. This time I go 70 microns deeper to compensate for the axial runout of the saw blade, in the hope that the thickness of the thin leg now will come out as 200 microns. Let's see. Oh yes, here she comes. Let's check the thickness. Should be 200 microns, and I left a bit for stoning the backside, so that went good. Now let's check the thick leg. Thick leg should be 500 microns. Oh yes, I think we can live with that. I will tighten this down very brutally. Centering microscope would be nice, but who has one? I don't. So I've got the 1.5 millimeter twist drill chucked upside down so that the cylindrical shank is towards the workpiece, and I think the best way would be to come down on the workpiece. I loosen the workpiece, come down on the hole, and then tighten the clamp when everything is in place. So here I'm machining that pin that has to be inserted or press fit into that 0.6 millimeter hole. Now before camera I already machined one and found it was a little loose in the hole, so I decided to make this 0.62 millimeter diameter. So that should work, hopefully. Just a very light chamfer in order to be able to press it into the hole more easily. Better not mess it up now, Alex. Careful. Carefuler. Even more careful. There we go. It's not fully on there yet. So this should be it. And here comes the idiotic part. This was late in the day and I felt very indestructible, but actually this is a very stupid operation, being able to lose the part and so on. But fortunately that worked out, even though it was kind of stupid to do this. Johannes will have to file fit this pin for a length, I guess. So something like this. Maybe? I don't know. Okay, so let's see a more close-up shot of the end result here. So this is what I could come up with. And that section here that we modified to more thickness indeed looks more beefy. It's just 0.1 millimeter wider, but since it's just 0.35 millimeter wide. That's a bit of an increase. The only thing I'm a little unhappy about is that there is a, let's see about the focus, there is a cosmetic defect here. I'm not sure if you'll be able to see that on video. A cosmetic defect that resulted from me sawing around that broken off drill bit here on the visible side of the lever. However, it's rather cosmetic than functional, so I hope Johannes will still be able to live with that. More important to me is the question if that modification will work out for Johannes, and we'll see about that in his video that I will link in the description below. So thanks a lot for staying with me, guys, all the way to the end of this video. I hope you found the one or the other thing in this video useful, or maybe inspiring for your own projects, and I'll see you on the next one. Thanks a lot. Bye.